I'm going to go a little different from this idea of, large numbers of patients and talk about individual patients, which is a little bit different from that aspect. I do have one major disclosure. That's Schering-Plough and Merck have supported the vast majority of the research. And I work very, very a lot with the National Research Council of Canada developing a neurotouch simulator platform really to do virtual reality surgery. So those are the two things that I've been predominantly involved with. Now, I'm going to talk about neoadjuvant pre-surgical temozolomide really as a model, and really talk to you a little bit about some of my thoughts and reflections about doing such trials. And I'm just going to outline just some of the results of a phase 2 trial where we looked at what is the influence of neoadjuvant preoperative temozolomide. In other words, what happens if you give temozolomide before an operative procedure and then look at what actually has happened to that individual patient, which is quite different than looking at large groups from that situation. With really a second focus, with that information, then we went and decided to go back in the lab. And I also run a lab there and basically look at that problem again. What happens in the patient, and then can you get that information into the lab and discuss what actually would happen if you modeled that situation. So basically the hypothesis that we started with was some of the variability in patient response to temozolomide is related to the heterogeneity of NGMT activity in glial tumors. And that's not brown working, but that's sort of what we started with. Now, one of the things that's always interesting to me, if you look at that initial STUP data, was you had three groups. You had this group here, which I wondered about, is it possible that their actual promoter is not very methylated in this situation? Is this a group where you actually have a situation where you have moderate methylation of a promoter? And in this group, you have a situation where you have a lot of methylation of the promoter. In other words, it's not one family. It's not a binary type of situation. It's a continuously moving sort of model based on how much methylation of the promoter you have based on survival related to this particular trial. So if you look at this, and this, you have to look at tissues to begin to get an idea about this. You can never, repeat that so everybody understands this, never have a completely methylated tumor. And the reason for that is, although you can have every single tumor cell that's methylated, all the endothelial cells are unmethylated, all the white blood cells are unmethylated, and every single other cell of the peripheral blood monocytes of any sort that is in your tumor are also all unmethylated. So you always have a small other sort of layer there. And so in that situation, you can never have a completely methylated tumor as far as the MGMT promoter is concerned. However, interestingly, you can have a completely methylated tumor, unmethylated tumor. And the reason for that is the tumor can be unmethylated. The endothelial cells are unmethylated. Your circulating blood cells are unmethylated, as are your white blood cells. So you can have a complete one band if you look at that. If you take a piece of human tumor out, put it in the lab, do all the information, and get that information. What's interesting is that what we think happens is you have this. You have a methylated tumor or an unmethylated tumor. And there's no mixture. You just have one or the other. So we have So we have a binary system. We either have it this way or this way. There's no mixing. Just do it once in one tumor patient and try to run it. This is what you get. In many, many of your samples, you get methylated bands and unmethylated bands. That's what you get. Can't take it away, that's what you get. So what happens here is, what is this unmethylated band? Well, it's unmethylated endothelial cells, unmethylated peripheral blood monocytes, unmethylated white blood cells, and possibly some unmethylated or partially methylated tumor. And so the percentage you get is based on this percentage value here. So let's think about this in a bigger way. We have a binary system now. You either have it or not. And if you have if you have no methylation, then you have lots of NGMT around, which repairs the DNA, and you have a poor response. If you have a lot of methylation, you have no MGMT around, and you have good response. I mean, that's how you think. However, you have all these other situations in between, and could they result in partial responses to temozolomide rather than this or this? And so you can calculate that. You just put the methylation over methylated and unmethylated, you get a number, and you can figure out what is the percentage methylation in that particular piece of tumor that you've taken out at the time of OR. And so what we decided to do was to run a trial to get a better handle on this. a number of other things. So what we decided to do was run a trial where we asked patients to go on temozolomide, 75 milligrams, once a day for 14 days, and we tried to control everything we possibly could during those 14 days before the operation to give time for the drug to actually work and get a handle on what the drug was doing over those days and all the repair mechanisms that may be going on. And then we did many, many different things. But then what we did is, using our fancy systems we have, is we looked at 4 different areas of the tumor that were distinct and tried to figure out what was going on in those 4 different areas. Now, we tried to keep patients on the same amount of temozolomide exactly at the same time every single day. So they all took it at 7 o'clock in the morning every day. We then had steroids, tried to deal with the steroids exactly. Every patient took the steroids exactly at the same time to try to deal with that problem. Every patient was on anti-seizure drugs to try to deal with that problem, and hopefully dealt with that as best we could in the situation that we did. So then what we did is we looked at multiple methods, and I'm not going to go through all these, I'm going to finish it here very quickly, just so you know what we did. Oh, let's go back here just for a second. We measured the TMZ and MTIC. This is the active, and this was then measured in another lab. We looked at the methylation, and this was done in my lab. We looked at the amount of MGMT protein that was available. We looked at the amount of enzymatic activity. In other words, you could have the protein there, but no enzymatic activity, and we looked at that. We looked at the O6 and N7 methylation, what was going on there. We tried to look at immunohistochemistry. It was hopeless. There was no relation whatsoever, so we just stopped doing it because we couldn't work. It just wouldn't work in our lab. And we tried. It just wouldn't work. So then what we did is, what I thought would happen if you took 40 patients, you asked 40 patients, will you go in this trial or not? 20 would say yes, and 20 would say no. Seemed like a logical thing to predict. Didn't happen that way at all. The vast majority of people wanted to go in, wanted to take the temozolomide. The second thing that we did is, obviously there's very few glioblastomas that you can wait around for 2 weeks. So there's not many glioblastomas in that trial. But there were some very small lesions that were present that we actually didn't think were glioblastomas, or probably anaplastic adenocytomas or something, and had no symptoms, had just presented with seizures or something. So we decided that those could be at least considered, and 4 of those patients ended up going in the glioblastoma, going in the temozolomide trial, and we only had 1 control in that situation. We had good extensive resections. We do big resections in Montreal, and there were no biopsies or anything like that because we needed lots of different tissue to do these experiments. So this is the temozolomide group. There were 34, 6 in the control, and these were the types of diagnoses that we had. We had everybody that we operated on had a tumor. We had no abscesses. We had no metastatic disease, and this 14 days, as best we could tell, had no impact whatsoever on surgery of any sort. So I won't go through all that, but that's what's happened. So what we found, this is what we found. Basically, there were some tumors that, if you looked at 4 different areas, they were completely methylated. Looked at other tumors, they were completely unmethylated. And then there was this mixture group. There were some methylation and some non-methylation in different areas, in different amounts. And so here's one example. This was one tumor, and we have a posterior part, and we could find no methylation at all. In this area, we found 15% methylation. In this area, we found 92% methylation. In this area, we found 50% methylation. So what is this tumor? If I happen to biopsy here, it would be completely methylated, not unmethylated. If I biopsy here, it'd be completely methylated. So it's a mixed tumor of some sort, having different areas. So if you look at the average of everything, we ended up with a 39% methylation. And the whole tumor, that was the average that we were able to find. So then, we'll go back here. So then what we found is if we looked at intratumoral variation of greater than 25%, about 20% of the tumors in the TMZ cohort were like that, and we had about 33% of the control cohort. So somewhere around 30% of the tumors have this big variation in the methylation percentage that we found. Now it gets very complicated. Every single tumor, we had the promoter methylation status in that specimen, and what you found is some were very homogeneous, some were not homogeneous at all. Then we had the data on the protein expression. There was some correlation, but it certainly wasn't clear that it was always correlated. And we had the activity, which was again quite different. So here we had different amounts of promoter methylation in individual patients, different parts of that individual patient, different amounts of protein expression, and different amounts of activity. So clearly, it was not a clear relationship as to what was going on in that individual patient if you actually gave them that drug for 14 days. And the same thing happens here. So what happens? Well, temozolomide goes to MTIC. So one of the questions was asked was, did the drug actually get there? Did it actually do what it was supposed to do? Did it change the methylation from an N7 to an O6 situation? So what you do with MTIC is it goes along and methylates the guanine at the O6 position. And then I'm just going to go through this very quickly. But the bottom line was that there was a difference between guanine being methylated and non-methylated. And if it's methylated, you get cell death. If you don't have methylation, then you get survival. That's sort of the idea. So what about the amount? Well, two things. One was that we only use 75 milligrams per day. So if you looked at the amount that was in the blood, it goes up very quickly to about, in 2 hours, that's your maximum dose. And then what happens, it goes down extremely quickly too. So in our patients, we gave the temozolomide before the operation. Now you got to remember, we gave it at 7 o'clock. The patient goes to the OR at 8. By the time the anesthetist puts these patients to sleep, by the time many of these patients were awake craniotomies and all that was done, we generally got the sample somewhere between 3 and 4 hours. By that time, most of the temozolomide was gone, and most of the MTIC was gone. In a normal situation, if you give the normal dose, you go up to about 8, go up here, and then it goes down. So it's the same sort of idea. So you get when you give temozolomide, you get a peak at about 2 hours. Within 3 or 4 hours, it's gone. It's been metabolized. Well, about ordinary patients then? We have lots of data on each individual patient. So this is when they took it. And this particular patient was number 34. You can see the temozolomide in the blood was here, goes up 2 hours later, goes down, and we got the specimens about here. So you can see we didn't get the specimen. We got the specimens with very low amounts. Look at the differences between these two patients. Same amount of temozolomide, etc. Much more temozolomide here in the blood, and much more MTIC. So despite the fact that individual patient gets the same dose, has been given the same dose for that period of time, there are still differences. The second thing, we had over 60 samples from brain. Not once were we able to measure temozolomide or MTIC in human brain at the time. And that probably was related to the fact we got it too late. By the time I got in there, it was just too late. All the temozolomide had been changed to MTIC and had already been metabolized and had already been cleared from the brain.
Even though it's promoted, or not promoted, but it's described as a drug that crosses the blood-brain barrier.
Now,
Blood-brain barrier, but it's
metabolized very quickly. I'll show you that. So here's what we were able to do. Because of the fact that I did not have lots of normal patients, in the sense that had patients who were glioblastomas, for example, and had been treated with this particular situation, we took a bunch of patients from our tumor bank to try to give us more information there. So if you remember now, we have these types of patients, and we took patients out of our tumor bank to try to get the numbers out. These patients, none of these patients had ever been treated with temozolomide. Every patient in this trial had not, they may have had a biopsy before, they may have had a partial resection, but they'd never been treated with radiation, had never seen temozolomide before. So you can measure all your, well, I won't go quite that far, but you can measure M7 methylated guanine relatively easily using HPLC, and this should never appear. O6 should not appear in normal tissue. So every time you gave the drug, if this appeared, then you found that something was happening related to temozolomide. The second thing is every time a molecule of this changed to this, the amount of N7 went down because you're not making no new DNA. So if you go from N7 to O6, the N7 goes down, your O6 goes up because you're dealing with that on a continuous basis. And you can measure this whole business. So what happens? First, surprising, untreated patients. What we basically found on treated patients, very, very rarely did you ever see any O6. Occasionally you did, but very rarely. But in treated patients, there was a lot of O6 present from that point of view. And as far as N7, of course, you've got lots of N7 in both groups from that point of view, both the treated and treated, because they're both, N7 is there, and so you got it both ways from that point of view. What was interesting here, though, is when you went from the untreated to the treated patients, you still had some patients that had predominantly N7, but there are a lot of patients that had N6 now. Now, what happens? Well, I don't going to go through this because there's a lot of data here, but let's start just with normal tissue. These are patients, and no patient who had operated on that we had normal tissue, this is either gray or white matter, did we ever see any O6 in an untreated patient. In other words, if you have normal brain, you never have O6 in normal brain. It just doesn't exist in your DNA that we have found in the patients that we operate on. However, if you have a tumor, there are some patients that have some O6. When you give temozolomide, there's all 6 appears in normal tissue. So normal tissue, DNA gets damaged by the temozolomide, or at least we have O6 methylation in normal tissue of human brain if you give temozolomide. It's there. The next thing we found, obviously, was tumor went up higher. So the more, we'll just stay with that from the present time. So what about low grades and high grade tumors? Because we had a bit of both in this situation. I'll just show you this. Rather interestingly, you get more damage with low grade tumors if you give temozolomide as far as O6 is concerned than higher grade tumors. In other words, low grade tumors, there is more O6 in low grade tumors after temozolomide treatment than there is in high grade tumors. The reason for that is unclear, but that's what happens in that aspect of it. So what about if the pathologist tells you it's a methylated or a non-methylated tumor, if they use the binary system? Well, the binary system works in the sense that if you have an unmethylated tumor, which means you have MGMT around, then basically what happens is you have lower O6 methylation. In other words, there's less damage that you can measure. If you do not have, you have methylated, in other words, you don't have a lot of MGMT around, you have higher amounts. I'm not going to go through this, but we also have information on IDH1 and other things associated with these tumors too. People are interested, I can tell you that. So what are the conclusions from this part? Well, I think that it's quite reasonable to do preoperative chemotherapy trials. They can be designed and can be approved by the ERBs on brain tumor patients to really test the biological effects of any drug, whether it's TMZ, on tumor biology. And I think that's where we all have to, as neurosurgeons, we all have to put an effort into it, because we as neurosurgeons can do these types of trials. There's a lot of intratumoral variation, MGMT activity, et cetera, and methylation, and that this heterogeneity can be assessed. Now, what we thought then, well, if the major problem is heterogeneity that we're coming up with, how do we do this in the lab? Well, we had a lot of information from other cell lines. So the U251 cell line, if you take it out and you do individual growing of one cell per area, you can grow as many cell lines as you want, of course, in that situation. So here's just some of the clones that we grew out. Incredible variety of methylation levels. You take one cell line, you grow it out, and you get all these different methylation levels. You go from almost 8% methylation to 100% methylation from one cell line, which suggests that in that cell line there are multiple different clones that are growing on a continuous basis. That makes sense from that point of view. So the next thing we did is we looked at pyrosequencing. Doing methylation is one thing. Pyrosequencing the whole promoter is another. Then you get all the data from that situation. So what we did then is we took every clone, or at least the vast majority that we looked at, and we did the pyrosequencing of the MGMT promoter, and then we did the parental cell line. Sorry, this isn't working as well as it is. Let me see if we can get it. Oh. Did I lose it there somewhere?
It stumped the experts.
Did I do a bad thing? Okay. Very simply, if you add up all the methylations of all the cell clones, you get the parental cell line here. So this is the parental cell line. This is all the ones added up. You get exactly the same situation. So when you get a methylation, you get the methylation of all the clones, which makes sense. All the clones are adding to the methylation depending on the percentage of those cells that are in there. So that makes sense. And so if you take clones, these are clones from one cell line, and you have 8% methylation or 91% methylation, they respond very differently to chemotherapy, as you would expect. That makes sense. Different clones respond differently to methylation. We did this with multiple cell lines. We grew up multiple cells ad nausea on every cell line you can think you can do, including medulloblastoma cell lines, and there's a very clear relationship. In other words, the more methylation you have, the more you're involved with this sort of process. So, and there's a very, very clear relationship with temozolomide and methylation percentage from that aspect of it. So the more, it just works well from that point of view, no matter what you do from all the cell lines you grow out. Now, you can do something completely different. Imagine yourself now with a tumor that's completely methylated. So we have a cell line, U373. They're all the same. Every clone is the same. In that cell line, they're all the same. So it's a perfect tumor. It's got all the cells, all the clones are all the same. Therefore, if you give temozolomide, you would think you get a really nice response. And in fact, you do. You get all of them respond about the same. So there's not a lot of variation within the clones from that point of view.
So you set up a model of a straw man and you knock it down.
You knock them down. So what you do, if you pick the appropriate cell line with all the clones being exactly the same, you can knock it out any way you want with MGMT, with
That has
temozolomide.
broad implications for experimental therapeutics and oncology.
Right.
You do that a lot with this line.
You think that the line is one line, which of course it isn't.
The human tumor has 100 million.
That's right. And you remember the very early experiments, you could grow 100 cell lines out of one tumor, easily. That's easy to do. It's when you grow 1,000 that's more difficult, but you can grow 100 without any trouble at all. You set it up, grow it tomorrow. It's easy, every one you grow 100 cell lines out. So the one thing that next was, what would be the effect of temozolomide on a heterogeneous population? So we used amount of temozolomide which would not kill all the cells. So what happens in this situation is you have this initial cell line that has all these different levels of different clones in it. You hit it with a small amount of temozolomide. Then you grow the resistant cells. Which clone survives? Of all the clones you have in there, which one survives? And so what happens is you can see that the one that grows out, whether you use U251 is different. The one that grows out with U351 is not very different, and U87 is very, very different. But I won't go into that too much. But this is what happens if you begin to do unassisted cluster analysis. So this is the cell line that we were talking about here, this one that's very, very resistant. Then we grew out the cell line that had been treated with temozolomide, and they cluster exactly the same place. So what's happened here is the same cell line, one clone, is grown out. All the other clones have been basically damaged or destroyed. The one major clone, which is already resistant, is the one we've grown out when we subtreat them. We've done that exactly the same with all the other ones, and if you look again, here it says interesting. The U87 here I'll show you. These two are in other words, you grow them out after you give them temozolomide. What happens is they all cluster together. There's some clustering going on here. In other words, it doesn't matter what cell line you grow out. If you do this dendritic relationship, they're all clustering to one particular group from that point of view. And this is where they were before. We're not getting the parental cell line out, we're getting a subclone out in this situation, which makes sense. The next thing was that the resistance or the epigenetic transformation that was occurring. So basically what we did is we did the exact U251 that was, I won't go into this too much, but basically it doesn't change, so there's really no epigenetic phenomena occurring here. There's not an epigenetic change in the DNA, it's that clone that continues to grow out. So if you hit it with temozolomide, the clone continues to grow out, it doesn't change its genetics, it's same clone. What happens if you mix them together? In other words, if you take, here is a U87 cell line. It's very susceptible to temozolomide because it's 100% methylated. You put in MGMT, so what you have in this situation, and then you stain them. Stain one blue, and you stain one yellow. So this one is the same cell line, but you've changed it. And then what you basically do is this cell line now should be, one should be resistant and one shouldn't be resistant. In other words, this one should be killed off, and this one should be resistant. And in fact, that's what happens. You know, this is U27, the parental, this is the control, and this was the MGMT. It survives it. So what if you mix them? Is it possible that mixing a MGMT, cell line that is same cell line that is expressing MGMT and one that isn't, what would happen? What would happen to the cells that are non-expressing the MGMT or expressing the MGMT? Would they change in any way? So basically what you did is you mix them up. When you mix, and here you can see they're mixed up here, yellow and blue. And I'm just going to show this. This is what happens. These cells all die because they're supposed to die. They have lots of MGMT. These cells survive because they have MGMT that we put into them. Then what do you do if you mix them together in a tumor? You mix them in a three-dimensional tumor. Would that change things from that point of view? And the answer is no. What happens is that if you mix them 50% in each tumor, three-dimensional tumor, and then you grow that tumor in a media, what happens is the ones that you have the MGMT in survive and invade, and the ones that you do not have the MGMT in, despite the fact they're in the same tumor, basically all die. So here you have a situation where no matter how you do it, it looks like there's some resistant clones that occur in certain situations, and these resistant clones survive the MGMT treatment from that aspect. So how do you put this all together? Well, here you have this tumor that has, 0, 15% methylation, 92, and 50% methylation. You give temozolomide. These clones survive, in this area survive, and that's what allows your tumor to come back. So conclusions, think about these types of studies. They're very powerful to provide information of how to go forward. And I think they should be an experimental platform for every new drug should be studied in this way. Because I can tell you, if the drug doesn't get in there, if it doesn't do anything, why are you going forward? Why are you studying that drug if it doesn't get in the brain and do what it's supposed to do? Why bother? Eliminate it immediately. Or get another way of getting it into a tumor that has a breakdown of the blood-brain barrier. Second, there's a lot of heterogeneity, and this is where the outliers come from. The outliers come from these tumors that are completely methylated, completely unmethylated, or this mixed group. And I would bet that this mixed group is in the center. That's the whole center group. The outliers are the ones on one end, and the other outliers are the one on the other end from that tumor. And maybe we should look at percentage methylation rather than positive, negative. It doesn't make any sense. These promoters are very, very heterogeneous. They're not plus minus at all. And then the temozolomide, at least in our experience, results in the production of a resistant clone. The other clones are killed off, and that clone survives. So that's what basically happens. So I'll just say there's a lot of people involved in these studies, but the most important people were really Jad here, who is here in the background, who did most of the work on the first group, and Ahmed, who did the work on the 06 and N7 methylation. Thank you.